Okay, so let's look at example 2 of optimization. This one is going to be just a little bit trickier. Find the points that are closest to the parabola, and I think something's missing here. We're given that the parabola is y squared equals 2x. I think it's in your notes. Okay, so we have to come up with a formula that would represent this. So if you recall, a parabola y equals 2x squared would look something like this. And the point 1, 4 would probably be in here. And we want to find the shortest distance between those 2 points, because we want to find the closest way to draw that from 1 to 4. So we're looking for the shortest distance. So we're trying to minimize the distance. So the question is, what formula could we use for the distance? So if you recall from, I don't know, 8th grade math, or I don't know where it's taught now, that the distance between 2 points is given by x1 minus x2 plus y1 minus y2 quantity squared. Okay? So this would be our primary equation. Our secondary equation actually is going to be what we're given. Y squared equals 2x is actually our secondary equation. Okay? So we know the point 1, 4. So we know x1 and y1. So x1 is 1. And for our secondary equation, we can also say that x is equal to y squared over 2. So we're going to do everything in terms of y. So x2, we can say, is minus y squared over 2 squared plus y1 then would be 4 minus y. So we don't have a value for that, so we're going to call it y. Okay, so this is what we're trying to minimize. Now, taking the derivative of this is going to be a little complicated, but we know this. If I were to ask you which is bigger, the square root of 27 or the square root of 29, without doing any math, you would automatically say that the square root of 29 is bigger. So if I want to minimize or maximize this, I can just kind of ignore the radical, because if I minimize or maximize the radicand, what's under the radical, I minimize or maximize the function. So to make my life easier, I'm going to ignore the radical and just maximize the radicand. So I'm maximizing, and let's call that value, let's call it z, is equal to 1 minus y squared over 2 squared plus 4 minus y squared. If I maximize, or in this case minimize this, then I minimize the function. So I am going to multiply this out. So I get z is equal to 1 minus y squared plus y to the 4th over 4 plus 16 minus 8y squared plus y to the 4th. Okay? Squaring that. Which gives me y to the 4th minus, okay, that should not be, I did something wrong. Okay, I did something wrong here, sorry. There's not a square here. The other one was squared. That kind of threw me off there. There's not a square there. The square is actually just on the outside. So sorry about that. So that should give me 16 minus 8y plus y squared. That's better. Oh, that number looked weird to me. So I get y to the fourth over 4. Negative y squared plus y squared zeroes out. Minus 8y plus 17. Now, I'm going to take the derivative of this with respect to y. So dz dy is equal to y cubed minus 8. The derivative of 17 is 0. Solving for y, I get y is equal to 2. Now, again, I need to know if that's a minimum. So I'm going to use the second derivative test to determine if it's a minimum. So if I take the second derivative of this, I get 3y squared. And I'm evaluating that at 2. So if I substitute in 2, I get a positive number. I don't care what that number is, I just need to know that's positive, which means that the function is concave up and therefore a minimum. So 2 is a minimum. What was the question? Find the point on the parabola where it's a minimum. So if 2 is y, I need to find x, and x is equal to y squared over 2, which would be 4 over 2. So the point where it's at a minimum, the minimum point here would be 2, 2. Okay? All right. That's it for example number 2. Please watch example number 3.